Hello! In this video, we are going to prove the following theorem. Suppose R is a partial order on A, and B is a subset of A. If B is a smallest element of B, then this smallest element is unique. So really, we're trying to prove that if B is a smallest element of B, then B is the only smallest element of B. Now, before we get into the proof, I would like to mention a few things. First of all, what does it mean for a relation to be a partial order? Well, if you recall, all that means is that our relation is reflexive, transitive, and antisymmetric. And second, what does it mean for B to be a smallest element of B? Well, if you recall, all that means is for every element x in B, we have that B comma x is an element of R. Okay, so now let's get into our proof. Now, let's suppose that we've already declared a partial order R on a set A, and let's suppose that we've already declared a set B where B is a subset of A. So now we want to prove that if B is a smallest element of B, then B is the only smallest element of B. So suppose B is a smallest element of B. Okay, so how can we prove that B is the only smallest element of B? What we're going to do is we are going to prove that every smallest element of B is equal to little b. So we're trying to prove a statement about every smallest element of B, so give me an arbitrary smallest element of B. I'll call it little c. And now we want to deduce that B is equal to C. Before we get into that, what does it mean for C to be a smallest element of B? Well, it means exactly what we have here. It's just instead of little b, I'm going to replace it with little c. Okay, so now let's get into deducing that B is equal to C. To start, we know that B is a smallest element of B, which means that this statement is true. And this statement works for every element in B. Now, because C is a smallest element of B, clearly that means C is an element of B. So since this statement works for every element in B, it must work for little c. So we can take x and replace it with c, and we get that B comma C is an element of R. In a similar way, because C is a smallest element of B, that means that this statement is true. And again, this statement works for every element in B. Now, because B is a smallest element of B, that means that B is an element of B. So, since this statement works for every element in B, it must work for little b. So, we can take x and substitute it for B, and we get that C comma B is an element of R. So notice, we now have that B comma C is an element of R, and C comma B is an element of R. We're just about ready to deduce that B is equal to C. And to see why, now let's use the fact that R is a partial order. What does that mean? It means that our relation is reflexive, transitive, and antisymmetric. In particular, it means that our relation is antisymmetric. What does it mean for a relation to be antisymmetric? Well, if you recall, all that means is if we have an ordered pair in our relation, and the inverse of that ordered pair is also in the relation, so say we have x comma y and y comma x, both elements of R. We have that if R is antisymmetric, then this means that x is equal to y. So in our case, because both B comma C and C comma B are elements of R, and R is antisymmetric, we have that B is equal to C. And so this completes the proof. The reason why this completes the proof is because we started out by being given a smallest element of B, namely little b. And we proved that little b is the only smallest element of B. The way we did that is we considered an arbitrary smallest element, C, of our set B. And we proved that our smallest element, C, must be equal to little b. And since C was arbitrary, this means that every smallest element of B must be equal to little b. And so yeah, that proves that B is the only smallest element of B. So yeah, that's pretty much the idea of how you could prove a theorem like this. And yeah, that's pretty much it for this video.